All right, I think we are live now. Hello, everyone. Welcome to MRI Together. This is the session on MRI hardware for everyone. My name is Andrea. I'm a graduate student at the University of Pittsburgh, and I will be moderating this session. So just a couple quick announcements. This session is being recorded and broadcast live. Transcriptions are available on YouTube. Please be aware of the code of conduct. You can read that on the MRI Together website. And finally, please put any questions in the Q&A rather than in the chat. You can upvote questions in the Q&A, and then at the end of each talk, we will choose the top questions to be answered, time permitting. I think that is all of the announcements. First, Lionel Broche from the University of Aberdeen will be speaking on open source imaging, a resource for accessible and open source MRI hardware. So take it away.
Okay, thank you very much. Okay. Hopefully you should see the screen now, my presentation.
Yes, looks good.
Okay, thanks. Okay, well, first of all, thanks to the organizer for allowing me to present this work today. And it was originally planned to be presented by Lucas Winter from PTB, but unfortunately he couldn't make it, so I volunteered instead, which I think is also part of open source, to be helping each other when in the project. Bear in mind that I'm a relatively newcomer to this project, so again, I hope it's a good demonstration that we can join in open source and be useful quite quickly. Anyway, so I'm going to present a project today which is called Open Source Imaging Initiative, OSI2, and how actually it can be helpful to the MR community. Well, it wasn't necessary, but I think it's always good to declare if we have financial conflict of interest, and I don't. Anyway, so the presentation I'm doing today is focused on how open source can actually help to tackle problems due to MR complexity, to help the dissemination of MRI as well, and to help to bring down MRI costs. And this is done, or what we hope to do is to do that through the OSI2 platform, so the Open Source Imaging Initiative platform. I'm going to give a few examples on how this actually is envisaged. During the entire presentation, I'm going to make extensive use of QR codes. I think it's easier to follow QR codes rather than links located nearby things. So if you have your mobile phone ready, you can actually grab the links as they pass by. Anyway, MRI is a complex technology which involves a lot of different specialties. So, of course, you have magnets, you have radio frequencies, you have the maintenance, per sequence developments, data analysis, quality management, clinical applications, and so on. And every single of these areas are actually. Can you hear me?
Sorry to interrupt you. We still see your PowerPoint application and not the presentation in full screen.
Huh? Okay. Okay, let me show again. Okay. Can you hear now?
Yes.
Can you see now? Okay.
Perfect.
So yeah, that was my presentation outline. So basically, as I say, MR is a complex web of different technologies, and it is challenging because each of these technologies require specialized skills. It's quite highly multidisciplinary, and because of that, it is the efforts for development of MR technology is quite scattered. You have limited access to hardware because of patented technologies from big vendors, which is not easily accessible. Those who have to deal with MRI research know that. And because of all these issues, the research centers that work on MR development, and especially for hardware development, tend to be scattered all over the globe. So that makes MRI quite a difficult technology to access, and not only for development, but also for patients. the fact that it's a technology which is difficult to develop and actually expensive is such that only rich countries are well equipped, and countries with a lower income tend to be quite poorly equipped. So there is quite a big discrepancy around the world. So this map is actually a map of the distribution of MRI scanners availability per million of inhabitants through the world. It dates back from 2013. There is a newer one from 2022. Unfortunately, it was very poor quality, so I didn't include it here, but the distribution is more or less the same. And it was recognized by the World Health Organization that MRI access is still a problem. Now, our approach to try and make MRI more accessible is to use open source, and I thought it would be useful to introduce the concept of open source, or at least what it means and what we can find definition or resources about it. Now, open source is quite famous for software, but it doesn't apply only to software. You have open source software, and you have the open source initiative, which is actually dealing with that, or which is helping with the development of open source for software. But you also have, more recently, initiative to develop open source hardware. I say recently because it really started to bloom around 2010. So there is about more or less 10 years, a decade or so of development on that. But their efforts are getting quite intensive, and there is certainly a nice trend which we hope will actually continue. And this is supported by many associations. And one of the prominent ones is OSHWA, the Open Source Hardware Association, which I give a link here. So these two are actually providing resources and definitions on how to recognize open source, and the guidelines on how to produce open source. So, well, I give a few definitions here, but the idea is that when it's open, you have the right to study, to modify, to distribute or sell. Selling is not forbidden in open source, of course, and you have the right to make. And these organizations and others are taking care of producing licenses that are allowing and favoring open source. Licenses is an important topic. I'm not going to present that in here because it's actually quite a lot of things to say. But it's a license that are the guarantee that what you're going to distribute will remain open source. And another confusion which is made a lot of time in open source is the possibility to embed open source into closed source system and conversely. So thanks to these licenses, it's possible, or for some licenses, it's possible to have open source devices which contain non-open source device. That's the case of Arduino, for instance. Arduino is an electronic board, which is an open source board. So you can actually find the blueprint, you can modify it and so on. You can sell it if you want. But it contains a microcontroller, which is not open source. And that's fine. The license allows this. Same for Tesla cars. Tesla car is certainly not open source, but the navigation system and the electronics, software inside is open sourced. And I heard that actually some of the hardware is also going to be open sourced, even though the car itself isn't. So it's possible to have open source system inside a closed source system and conversely. So licenses allow for this. And of course, it allows for sales. Now, how can this help? Well, basically, open source is a great way to contribute or to help contribution from the community. So it helps for crowd-based approaches, which help with dissemination. It also helps to get contributions. So with open source, basically, you can contribute in many ways. Of course, you can contribute with money, either by donating or by favoring the grant proposal. You can give some of your time to help with projects. You can provide open source devices or help with the development of devices. But it's also a rally point, so it helps people to know where to go if they want to produce something, or if they want to know more about how to do that in an open source way. And very importantly, it's also a great technology accelerator because you don't have to reinvent the wheel every time. If you want to make a new MR system, you probably don't want to have to reinvent the RF system, for instance, because it's very well known, and that's maybe not what you want to innovate on. So open source has a great role to play in MR and in other technologies, as a matter of fact. But what's interesting for us really is MRI today, and the open source imaging initiative has a big impact on MRI. It wants to make a big impact on MRI by producing open source designs, either software or hardware, on via the open source imaging initiative platform. We hope to really boost community building and also creation of new businesses and so on by sharing information. You also boost research by avoiding to reinvent the wheel, as I said. You help people to self-educate by sharing education content. You improve the quality and availability of devices, and so on. So it's all these aspects that we want to be to boost via this platform. So what is the platform itself? Well, basically, again, there is a QR code here if you want to reach the website, but I made a copy here. So if you go on the website, basically what you will see is a repository of different projects from various places. These projects are well organized, and if you click on one of them, you can actually see what it is about. So you have projects about everything. One example is the cozy measurement frame system. I took this example because I'm actually in the process of building one myself. So what I did is I went on this web page here. It gives me a link to the resources on the bottom right in here of the screen, where you can have a link to the GitHub page. So you don't need to go to this web page to make your project. If you have a project which is on GitHub already or on the platform, you can ask this platform or open source OSI2 to make an advertisement of what you're doing, basically. So you can ask it to redirect it, redirect this page to wherever you have your information. And from there, you can get the information you want to build whatever you want to build. So basically, to have an open source device, what you need is a bill of material, possibly with the vendors. That's the case for this cozy measurement system. So you actually know what kind of cost the device will have. You need the blueprints, of course, electronics and mechanics, software, some assembly instruction to help with making the device, the manuals to use it, and here you also have a community portal. So that's the basics minimum for a nice device. If you have less than that, you can always share, but it's good to have something which is as complete as possible. Guidelines are available from the OSHWA Open Source Hardware Association if you want to know how to do that nicely. And if you look through the OSI2 portal, you will see a lot of different devices for MRI. So you will see magnets. As a matter of fact, there will be some of the devices presented later in this session. You will see radio frequency amplifiers. You will see gradient amplifiers, shim amplifiers, so shim power supplies. You will see some coil design software. You will see also some consoles. You will see a pulse sequence development. So there are lots of elements actually around MRI. And as a matter of fact, there is everything needed to build an entire open source MRI. And that is a project which has been launched some time ago, called OSI2.1, which aims to build an entirely open source MRI system as a demonstrator that it is possible, but also to lead the market and to actually explore this the aspect of open source on clinical MRI from a realistic point of view. So I give a link here again. So OSI2.1, actually this open source system has really started OSI2 platform had really started in 2016, so quite some time ago. It was a joint effort from the beginning. You can see here 52 authors, 35 institutions, so quite a lot of people actually started this initiative led by Lucas Winter and others. And the idea was really to make this portal for the community. In 2019, there was the first in vivo imaging of prototype scanners. So again, Tom will say more about that next. Later on, 2022, that's when OSI2 really started. So the scanner started to be sufficiently refined to be documented and to be proposed as a system. And as a matter of fact, it was actually shown at the ISMRM conference. Those of you who were there last ISMRM may have seen the system in the corridors. It's actually very impressive that this was managed to be done. And recently, there's been a successful application to Euromet, which is a meteorological institute, which provides grants for meteorology projects. And the idea is to demonstrate that not only it's possible to build this open source MRI system, but actually the building process can be sufficiently reproducible to become a clinical device. The idea is really to go to and reach a stage where we can demonstrate that open source is not just a side project that people can do for fun, but it can really lead to medical devices that could be distributed into hospital and built by manufacturers. So the next stages will be, well, making sure that this can be done. That should happen in the next few years, and hopefully to continue with clinical applications and certification processes. Sorry. So why do we do that? Well, the idea is really that with open source, in software at least, we know, or it's been demonstrated from software development, that this really pushes dissemination, building community, and it's really is something that's been adopted quite quickly, or at least in the years 2000s, by companies. And those of you who may have seen the start of open source software may actually remember that it was welcomed with a lot of skepticism by large companies at the beginning of the years 2000. And obviously nowadays it's a norm. So that's, I hope, will become the same for open source hardware. And that will bring, hopefully, affordable and available devices, making it available to other people to build, to actually make it easier to diffuse technology. More efficient as well, and that also is something that has been seen with software. Sharing software via an open source model is a great way to troubleshoot issues, to improve the quality of the code, and to define meaningful norms and ways of standard of practice. So we hope, we expect this to be the same in hardware, but it's also, and quite importantly, to build bridges. If you have a project at the moment which you think could be an open source project, or would require some knowledge that you don't have on particular devices, and you're looking for partners, or you're looking for people to maybe to give you some advice on how to license your system, on how to document it, if you want to share it, this kind of community is really the place where you should go. And that's what we also aim to do with OSI2. The graph that I'm presenting here is from a publication that was done in 2019, again from the consortium, and demonstrating that the expected cost saving if we swapped MRI devices from closed source to open source, like for like, would actually be quite substantial over the time. So in 10 or 20 years, that would be billions that you could be saving just by doing that. So it really has a real impact. And the last point is really that it's fun to share and to be able to have other people's contributing to a project that we like. So I really think that is something that you will find useful, and certainly something that drives me into this project. Anyway, again, I'm certainly not the person who is most visible on this project. There are many contributors who's been working hard to make this happen. It's difficult for me to list them all. You see some here. I hope that you will join this initiative. I think it's really something that can and will change MRI developments in the future. Thank you for listening to me, and well, I suppose it could be time for questions now.
All right, thank you so much for the excellent talk. That was a great way to get started and kick off this session. I don't see any questions yet. Feel free to ask questions. In the meantime, I have a question. I guess my question, let me try to think of the right way to say this. How do you picture like from where it is now to maybe clinical use, and like how challenging will that path be?
There are a few steps in between, and It's something that I've been working for some time because I am also working on a new technology called field cycling imaging, and I'm actually reaching the same stage, the same stage of development. The next stage, really, once you know that you have a device which works, which can be built, and which built is reproducible, is to demonstrate that it has a clinical use. Because you cannot really do a clinical certification if you don't have a clinical use to propose. The clinical certification process requires you to provide targets for a particular clinical need. So the first thing is to identify the clinical need that can be answered. And open source is great for that because it can be tailored. It allows to tailor technology to particular needs. So if you find that the device that you've made is not quite what it needs, you have all the information you need at hand and the community to help you to modify it and make it specific. We see that a lot with Linux, for instance. You have a lot of distributions that answer specific needs. And I suppose the same should happen with open source hardware. So you have a lot of clinical needs. We probably are not going to see one device that solves it all, which is more or less the approach that you see with high field, simply because it's very expensive. But if you go for devices that are not expensive and easy to reproduce, then it's probably going to have devices that are really specific to particular needs. So there's probably going to be this diversification of the project, or at least that's what I see, which will target particular clinical needs. What we will need is to make sure that all these devices or all these initiatives work together to help with the clinical certification, because it's a very tough process. And part of the reason is because it needs a lot of documentation for the auditors to actually understand how the device works. Again, the fact that it's open source may actually help with that. But anyways, what I see is really finding the clinical needs, adapting the device to the needs, and then clinical certification. That's what I see at the moment from looking at a crystal ball. It's always hazardous to read the future, but at least that's what I see.
Thank you. No questions yet, but if you have any questions for Lionel during the next talk, feel free to keep putting that in the chat and we can have more discussion after the first two talks. So I think I'll go ahead and get started with Tom here. So next up, we have Tom O'Reilly from Leiden University Medical Center, and he will be talking about open source MRI magnet design.
All right, can everybody see my slides?
Yeah.
Perfect. Thank you for the introduction, and I'm really looking forward to hearing some feedback from the people in the audience. So please feel free to rudely interrupt me with questions if you have any. So I'll start off with just giving a brief overview of the various components of a typical MRI system. Obviously, the complexity of these systems will vary quite a lot between different system types, but this is just a very, very basic overview of what such a system looks like. So we have the host computer. This is typically what the radiographer will sit behind when they do the MRI exam. This computer talks to the spectrometer, and the spectrometer is the device that will turn your software commands into the various MR waveforms that are necessary to create an image. And it will also acquire the signal or digitize the signal and transfer that data back to the host computer for the image reconstruction. The spectrometer talks to the RF amplifier, which amplifies the very weak RF pulses that come from the spectrometer into something that's actually strong enough to create an MR signal. This waveform is transmitted into the transmit coil. There's a little one visible here in the image. And then it can be the same coil. At low field, it often is the same coil. At high field, typically you will use a coil array. But the data then comes from the sample into the receive coil and into the preamplifier, and then finally back into the spectrometer. And then to actually make an image, you obviously need to drive your various gradient coils. So the same weak signal from your spectrometer is transmitted into the gradient amplifier. It's a very different technology because it's really essentially operating at DC, and it's trying to generate the currents that you've asked for in your pulse programming environment into the gradient coils, and that's quite tricky to do. So the gradient amplifier is connected to your gradient coils. They're not visible in this image, but they're integrated into this white cylinder that you see on the side. And then obviously you have the magnet itself, which is visible here is a holeback array, which magnetizes the signal, magnetizes the spins, and allows you to actually interact with them. So I'm going to go through the various bits of this system, show the open source, or some, it's by no means complete, but so some of the open source hardware that's available for each of these components, and then show what we've been able to do with this system so far. So low field, nowadays when we talk about low field, it's typically less than 0.1 Tesla, although there are some vague boundaries. The magnet designs for those kind of fall into two broad categories, typically permanent magnet based. And then in the permanent magnet based systems, you have the holeback magnets, which are typically a little bit smaller and lighter than the yoke magnets, because the yoke magnets have an iron yoke, which is necessary to contain the magnetic field lines within the structure. Both have their pros and cons. The holeback arrays are very lightweight. They're easily constructed by hand because they consist of a lot of small magnets that are quite easy to manipulate. But because of their intrinsic structure, they do suffer from having a smaller opening through which the body part can be inserted. And they typically, although not absolutely, tend to have a lower homogeneity than equivalent yoke magnet systems. Yoke magnets, on the other hand, have a higher field strength. What's really nice about yoke magnets, and this is also why some of the products that are closer to market and products that are on the market will use a yoke magnet, is that they intrinsically allow much more access for the shoulders, because they have this rectangular shape, whereas holeback arrays typically have a circular shape. So the shoulders have to stay outside of the main magnet structure. The disadvantage of these is that they do have the heavy iron yoke, so these typically will be quite a lot heavier, hundreds of kilos heavier than the holeback systems. And this is a personal thing, and people will probably disagree with me, but I typically they are more difficult to construct because you have a single large magnet piece or two large magnet pieces that need to be placed inside of an iron structure, rather than having the easy magnets that are easy to manipulate. So the rest of the magnet talk will be about holeback arrays. I know that Clarissa is also giving a presentation later on the tabletop system, which will use a yoke magnet, so you kind of get to see the construction process of that as well. So holeback arrays or typically when we talk about holeback arrays for low field, we talk about cylindrical holeback arrays. And in these cylindrical holeback arrays, if you rotate your magnetization of the individual magnets that make up the array twice over the circumference of the magnet, in theory, that creates a perfectly homogeneous magnetic field that's oriented across the bore. So it's different from conventional systems where the magnetic field is down the bore. This is really only true for infinitely long arrays. And as soon as you make the magnet shorter, then you have to then you suffer from severe inhomogeneity of the system. And this is something that you have to compensate for. So one of the things that we've worked on is a method for compensating for this inhomogeneity that's introduced by having this finite length magnet array. And we do that by allowing the ring diameters of our magnet to vary along the length. So to compensate for the field drop-off effect, we basically have these smaller rings on the edges of the magnet, and those smaller rings are associated with a stronger magnetic field. And by having a stronger magnetic field on the end than in the middle, you're compensating for this magnetic field drop-off that you have along the length. So this works really well. If you want to have a go at it yourself to try and design a better magnet, then the code is all available on GitHub. You can scan this QR code or click on the link. And you just define the number of rings, the spacing between the rings, what ring radii you want, and then it will try and design the most homogeneous magnet for you. In this optimization, we do treat the magnet as ideal dipoles. This is perhaps not entirely true and not entirely correct, but it does allow us to keep the code open source, because if you want to do it exactly, you really have to validate your design using finite element method simulations, and those are very complicated to program, and there is very little open source material available to do that. So we tend to stick to using these dipole approximations of the magnet, just because it's much easier to open source code that way, and it works very well. So this is the new system. So Lionel mentioned it already before, but this is the new system that we're working on. It's a 30 centimeter bore holeback array. It's 50 centimeters long. and it has just over 4,000 magnets in them. And the homogeneity is much worse than what you're used to at high field, but we are at a lower magnetic field strength. So in terms of hertz, this is actually not that bad. And also in terms of image distortions, the field inhomogeneity is not too bad, but it's something that you do have to correct for in post-processing. So this is a little bit of the disadvantage of using these smaller low field systems, is that you do have system imperfections that you have to deal with. And the weight of the system is around 115 kilograms. And that makes it fun because you can move it around, and I'll show you more on that later. So these are the various ring configurations. I don't expect you all to write this down, but it's just to show you that the structure and the larger ring diameters in the middle and the smaller ring diameters. So you have your optimization, or the results from your optimization, and now you have to go about actually designing your own open source magnet. There's a lot of magnets to draw. There's about 4,000 of them. I would recommend using a program like FreeCAD, which is not only open source, but it's scriptable. So you can actually write a little script to draw every single one of these magnets. Otherwise, you will go bananas trying to do that, and you will likely also make mistakes. So FreeCAD is definitely something that's recommended if you want to have a cheap and free CAD software to do this work in. Because we make the rings out of plastics or generally soft materials, because it's easier to work with and easier to manufacture, the rings will flex. So when you're positioning the rings, you have to make sure that the rings are in a correct position. Now, if you position them only on the outside, your ring will start to bend. And because we're really trying to get the homogeneity into the order of hundreds of ppms, we really have to do a good job constructing things. So we also have to add threaded rods on the inside, and this prevents the flexing of the ring. So this is an improvement on the new system. The gradient coils will get placed on the inside, so we have to include the design for that to accommodate that. And then we put the shim trays on the outside, because no matter how well you build the system, you will have to shim it. And that's true for high field systems too. So how do you actually go about making one of these magnets? This is a demonstration of Lucas Winter building a copy of our system in Germany. We use a CNC machine. It's expensive. We used to use laser cutting, but actually laser cutting is really not up to scratch. So we switched over to CNC. It's slow, but it's much faster than 3D printing and far more accurate than 3D printing as well. So this is, again, where the investment into the materials actually pays off in the end. The accuracy is very good. It's higher than we need to. So this is something just to find your optimal in terms of cost and performance. And then once you actually fill the magnet, put all 4,089 magnets into your system, and you stack all the rings together, you actually have to measure the magnetic field. And this is a project that Lionel was showing earlier, and it's us mapping the magnetic field of our magnet after it's finished. It's the 3D positioning system called the COSI measure. Again, the link is available here. We use a Hall effect sensor to map the magnetic field in relatively high precision. And then based on that, based on the data that we get out, we can fit spherical harmonics to that data, which just help us reduce any further noise of it present on our data. This does need to be done in a temperature stable environment because it takes quite a long time to map the magnetic field. And if the field is drifting while you're mapping the magnetic field, obviously that's going to distort your measurements a little bit. So on this system, after putting all the rings together and not shimming yet, so this is before shimming, just a raw data map, we were at 7,000 ppm over 20 centimeters. And remember, in simulations, we were about 700 ppm. This is quite typical, seeing this difference. But after just one iteration of shimming, we were able to get much closer to what the simulated magnetic field performance was. So now we have a magnet. What else do we need? Well, we need to design some gradient coils because we actually want to do imaging experiments. So we've developed an open source tool, GUI, for designing gradient coils. You can download it here. This is by no means the only way of designing gradient coils. And in fact, there's another presentation coming up later, which will show a different method, CoilGen, to generate your gradient coils. So I recommend sticking around for that. And then you want to build your gradient coils because well, you need to know where to put the wire. Well, you know where you want the wires, but you actually need to be able to put them there. So this is where 3D printing has really come into its forte over the last few years. We're able to print very large structures like the gradient coils. And after cleaning the 3D prints, because they're never perfect, we can just click copper wire into the paths of the 3D print, and then we mount those 3D prints inside of the magnet. To drive the gradient, you need a gradient amplifier, as I mentioned before. And again, we've developed an open source gradient amplifier for which all the schematics and the PCBs can be downloaded from our GitHub page. It's 15 amps and 13 volts, which if you compare it to commercial systems, it's incredibly low because they're able to usually put out a kiloamp and a few kilovolts. But because our gradient coils are so much smaller, because our system's so much smaller, we don't need anywhere near that amount of current. And by keeping this voltage this low, we can actually operate our gradient amplifier on car batteries. So if you're operating in regions where the electricity grid is not very reliable, this is a great option. Again, by no means the only gradient amplifier, open source gradient amplifier out there. In fact, the GPA HDO is also a very nice project, and I think the tabletop system that Clarissa will talk about later uses this or a derivative, or this is a derivative of that system. But again, those designs are fully open source and available on GitHub. RF coils are very easy at low field because we can just use solenoidal coils, and we have no B1 wavelength effect, coil loading, SAR, no nothing. So our coils are very simple. The only thing that we do suffer from is that coil arrays will not give you better SNR at low field. A very long reason why, but essentially the noise in our coils is the dominant loss mechanism rather than the body loss mechanism. So it pays to build the best coil that you can, the most sensitive coil that you can, rather than building a small coil, as you would for coil arrays. To drive these coils, you need an RF amplifier. When we started off this project, we had no idea how much power we actually needed. So we massively over-engineered our RF amplifier. It can output a maximum of 1 kilowatt, but typically, even for a 180-degree pulse at our field strengths are at maybe 4 or 5 watts. So this is a little bit of overkill. If you do want to copy it, feel free. The schematics are available on our GitHub page, but it's way too powerful. So at the ISMRM last year, get his name. The Easy MRI RFPA was presented. It's a 200-watt system. It's a very flexible design. Again, fully open source. If you want to play around with something that's a little bit lower power, then that's available for you. But actually, this is where we start to challenge you. If we want an RF amplifier with an absolute maximum RF power output of 50 watts, operating from 1 to 5 megahertz with a 50 dB gain, is this something that the community will be willing to design with us so we can have a lower power system than we have at the moment and become part of the open source community? Again, the preamplifier, this is something that at the moment we don't have because there are very few commercial options. The commercial options that are there are expensive, and they typically don't have very, very good performance because they're designed for systems of 1.5 Tesla and upwards. But for us, at low field, we typically stay below the 5 megahertz frequency. So this is 1.5 Tesla is at 64 megahertz. So this is much beyond the frequency range that we need, and they typically work less well at these low frequencies. So again, if this is something that you guys have experience with, please feel free to share that experience with us and see if we can integrate that preamplifier as part of the open source imaging initiative effort towards a truly open source MR system. The final piece of the puzzle is the spectrometer. So we recently published a few papers on this system. It uses the same software-defined radio as the Okra system does, but the software base for it is different. So we call this the Marcos system. This is a $600 device that you can just buy from pretty much any electronics vendor. It has 2 transmit channels. It's got 2 receive channels. And if you want to drive some gradients with it, you do need to have this external digital to analog converter board. This particular one was designed by Marcus Prier, but there are others available also. The programming language for this is Python based. It's fully PulseSeq compatible, and the software is very much open source. So again, if this is something that you're willing to contribute to development for, please feel free to get in touch with any of the people involved in this project. So if we go back to the MRI system overview, we have open source options for every single one of the components in the system, apart from the preamplifier. So again, if this is something that you're willing to help us out with, please feel free to do so. And I'm putting this in gray because I'm about to show some images, but because of component shortages, we took our DAC board to Uganda with us to build a system there. But we've had to leave it there, and we've not been able to replace the DAC board. So at the moment, we're imaging with a closed source spectrometer. But we were able to acquire some in vivo images of the brain on this system. This is 2 by 2 by 3 millimeter resolution, and they come out pretty good. Scan time is a little longer than you are used to on commercial systems, but considering this image was acquired at 50 millitesla, without any fancy AI reconstruction, just the CPR for Bezier distortion correction, it's not bad. For CSF, if you want to only look at the CSF, and this is something that's relevant for the research collaboration that we have with the people in Uganda who are looking at hydrocephalus, you can run these CSF only scans, and you very much see where the fluid buildup is in the brain. So again, for a 50 millitesla system that costs about $20,000, $30,000, it's not bad. And despite the large B0 inhomogeneity, we're still able to acquire gradient echo images for most of the brain. We only start getting a little bit of loss towards the bottom of the brain near the cerebellum. So this is the system, the OC1. It's the magnet. The mass of the magnet's around 125 kilos, including the gradient coils and the shims, etc. It consists of a set of 3D printable gradient coils, RF coils, a few designs available too, and the electronics too. And we target the cost of the entire system for 20,000 euros. We're happy to share as many of these drawings as you guys want, but we do have to do this in the context of a research collaboration for various reasons. So if this is something you're interested in, please get in touch with us. And like I mentioned earlier, we actually did just come back from Uganda, where Jones Obongolok, who's been very, very large proponent of the open source effort and the low field effort for increasing accessibility to MRI, invited us to his lab, and we were able to construct the system, the entire system, and acquire images in, I think, 11 days. So that was pretty exciting. And in terms of portability, again, this is something that Lionel mentioned earlier. But this is we were able to put the entire system in the back of a van, drive it onto a ferry, and give a demonstration of the system at the ISMRM. So we're slowly spreading around the world. We've just received funding to build a few more around Europe, and then Josh Harper is also going to build one in Paraguay, hopefully several, but at the moment funding is in place for one. But if this is something that you're interested in joining us, please get in touch. Obviously, I have a lot of people to thank. I can't put them on this list, but I also want to thank you for your attention.
Awesome. Thank you so much, Tom. That was a great talk. It's really cool to see what can be done. Those images looked awesome. So we have one question for you. Did you experience major problems in continuing your work caused by the global hardware component chip shortage that's been going on for the past couple of years?
Yeah, absolutely. Excuse me. So definitely with the DAC board, this is something that we've experienced. So it seems like most of the components are coming back into stock, but any analog to digital converter or digital to analog converter just seems to have lead times of still months, if not years, and also very, very expensive. So these parts have increased fivefold in price. So this is actually the main area that we've noticed it. Most of the other devices have remained in stock, but ADCs and DACs have been an absolute nightmare.
Also, probably just a few years ago, that cost would be quite a bit lower.
Yeah. Also for everything, also the capacitors for building RF coils and things like that, they've gone up 3 or 4-fold over the last 5 years. It's a magnet. We started this project in probably built the first magnet in 2017 or 2018, and I remember paying 70 cents per magnet, and we're now paying €1.41 for the exact same magnet. So as you know, and this is quite a big part of the cost of the system, because you have 4,000 magnets. You've gone from $3,000 to $6,000 for the magnets because of that.
Here's more of a comment from Lionel. He says, 11 days to build a functional MRI system is impressive. Absolutely. So did you sleep at all during that time?
They were quite long days. They were quite long days also because we had some logistical issues. The glue that we need to put the entire system together is not a glue that the customs people in Uganda were familiar with, so it took a little longer to process. Same with the gradient amplifier. You're importing highly specialized equipment into a country that has not had to import that before, and that threw up some challenges. But overall, it was a relatively smooth process.
So I'm wondering, you mentioned you could use a car battery. The systems that you currently have implemented, are those portable systems with a battery, or are those typically being plugged into the wall?
So the RF amplifier is pretty much the only part that at this moment in time is not, we can't run off a car battery. So we couldn't run the entire system off a car battery anyway, not without an inverter anyway. But we typically don't run the system of car batteries, mainly because you have to recharge them, which is a little bit annoying. So if you can get away with it, just use a regular power supply, would be my advice. It definitely makes the whole system more stable, but you could.
Another question, do you keep particular MRI sequences in mind while designing such systems?
Yes and no. I think you have to be honest with yourself. So that when you're designing a magnet, mainly talking about the magnet because the magnet is it kind of determines the rest of the system. When you're designing a magnet, the trade-off that you're always making is field strength versus homogeneity. They're very closely linked. So I could design a system that's 10 times higher in homogeneity, but it's got a field strength of 10 millitesla, so you're not going to get any SNR. And then you have to ask the question is, what's the difference in system performance that I get for a system that has 50 ppm versus a system that has 500 ppm? Can I actually run different sequences on that system? And the answer is very often actually no, you can't, because the spin echo sequence makes you very, very robust to B0 in homogeneities. You can run a gradient echo, sure, but if you really want to do fast gradient echo imaging, so you want to go towards the steady state free precession, the SSFP sequences, those SSFP sequences need line widths on the order of hertz. And you have to drop the field strength of your system so much in order to even get close to those line widths that it's just simply not worth it to do conventional SSFP sequences. There are ways to do SSFP in more inhomogeneous fields, but honestly, the answer is there is very little sequence. There's very little difference in the sequences that you can perform at 1,000 ppm or 1,000 hertz, I should say, versus 10 hertz. I think there's a limit beyond 1,000 hertz where you start suffering from, are my RF pulses short enough to excite the entire bandwidth and things like that. And that's a different problem. But from a sequence point of view, there is no difference between 1,000 hertz and 100 hertz. Not really.
Okay, another question from Lionel here. Let's see if I can read the whole thing. Permanent magnets tend to be quite variable due to various process issues. Do you think it would could be possible, or sorry, do you think it could be useful to map the field of individual magnets and use this to optimize their position in the Hall-Bock magnet? It would be time consuming though. Yes.
It would be very time consuming. If Lionel comes to light and measures the next batch for me, then yes, I will very much consider that. One of the benefits of using 4,000 magnets is that there will be some variant that you will average out some of that variance inside of the magnetic field just due to the sheer quantity of magnets that you have. But when you have certain set biases, like if you get magnets from 2 different batches, they will all have a standard deviation around an average, but that average will be different between batches. So if you can use all magnets from the same batch, that's the main thing to consider. And then other than that, you can just shim it out, especially the inhomogeneity caused by magnets of varying strength. That's quite a low order perturbation on the magnetic field, and that's quite easy to shim out using magnets, using shim magnets.
Can you typically get the quantity that you need from one batch?
Yes. Yeah. I don't know what the actual number is that you can get from a batch, but the way they do it is they just make a giant plate of material and they cut your magnets to size. We've never had, I believe we've had 10,000 magnets from a batch, and they didn't bat an eyelid at that. So you can get quite large quantities, although I don't know exactly what that number is.
Another question that I have, what's the largest bore size that you've simulated so far?
30 centimeters. So that's it's because of this. Yeah, it's more or less true. Because of the issue with the Hall-Bock array being that you can't fit the shoulders in because of this cylindrical design, it's either you do 30 centimeters or you do at least 60 centimeters. And the increase in magnetic material that you need to make a magnet of 60 centimeters is so huge that I kind of have been too scared to run those simulations because not that I don't think my computer can handle it, but it's mainly I'm not sure my fingers could handle putting so many magnets into holders. We built quite a few of these systems now. We together with Lucas Winter, he's got one in Berlin. We just came back from Uganda, and then we've had 3 or 4 prototypes here in Leiden. So I think probably put well over 20,000 magnets inside of magnet holders, and the fun wears off after a little while. So to do such a big build is not something that I think I'm willing to do at the moment.
Yeah, I could imagine. So I think that might be all the questions for you, but I do want to offer, there was a question from Gaurav for Lionel earlier. Lionel, do you want to elaborate on that at all, or do you think you said everything in the chat?
No, it's all in the chat. But maybe one more question from me is about the coils. So you mentioned the problem of bandwidth with the coils. It's something we've seen here working on low-field systems. It's interesting. It brings a lot of problems. But I was wondering if you think that coil arrays could be a way to improve that. So instead of having coil arrays that discriminate spatially, you could have coil arrays that discriminate frequentially. So you have different coils, different frequencies. Is it something that you've explored before?
It's just thinking about it, but yes, I agree. The only thing there is that it would restrict the frequency encoding direction. It does restrict your system, but for instance, on Clarissa's system, where she has the built-in gradient, you always know what the readout gradient is going to be, and in that case, I definitely think there it makes it's definitely worth exploring. There are also ways of getting rid of the or at least the majority of the image shading caused by the coil bandwidth. We're just happy to share the data with everybody, but not in time for this. It wasn't part of the presentation. We're just working on a publication for that, but it's basically if you look at the noise distribution that is picked up by these high Q coils, you can that noise distribution is almost one-on-one matches the coil bandwidth. So you end up having the most noise at where your coil is 50 ohms, and then away where the bandwidth, where you lose sensitivity of the coil because of the bandwidth effect, you also lose noise. So if you calibrate your data based on this noise distribution that you measure, you can whiten the noise. So because the noise should be white in the MR experiment, you whiten the noise, and that gets rid of the majority of the image shading caused by the coil bandwidth. So it's a very, very simple way of dealing with that issue. If it doesn't make sense, there's a paper in the upcoming Magma-ish, I think it's or NMR and Biomed paper, special issue on low field that will discuss this in more detail. But happy to give sneak previews if anybody wants.
All right, well, thank you both again for the first two talks here. I think we can move on. Again, if there are any further questions, feel free to put them in the Q&A or in the chat for Lionel and Tom. So up next, we have Clarissa Cooley from Harvard University, and she'll be talking about her tabletop MRI scanner.
Hi, everyone. Slides. Okay, so we're here in the lab. Jason Stockman is here with me. He's sort of, he's helping me with this talk. He did a lot of the work on this system, and he's also going to be helping me do a demo later. This talk on the original design of the scanner, which was published in JMR a few years ago. And you can see that on the author list, we have several different universities and organizations. This was a huge collaborative effort to design these low-cost tabletop scanners for education. So here at the Martino Center, at MGH, and at MIT, we really worked on sort of the system level design and the construction and implementation of the full scanners. At Freiburg, they designed the gradient coils that we'll be showing. The Chinese Academy of Sciences designed the magnets that were used for the educational scanners. And then at Stanford and also Procyon Engineering, they developed the Medusa console that we showed in this paper and we'll be using for the demo. So the goal for this project was to build a set of 20 small educational MRI scanners for a teaching lab at MIT with a budget of less than $10,000 per scanner. The design constraints for this were the price, $10K per scanner. The imaging volume was 1 cubic centimeter, and it was meant to be a portable design, so all the system components are contained on a cart that can be moved around the lab. And also, we tried to make it low maintenance, so only passive air cooling. We don't have any forced air cooling or water cooling, and also operating from a standard power outlet. And lastly, it's an open, transparent design so that it's fully accessible to the students, and the design, all components of the design are accessible to the students, and also open for them to be able to implement new projects that can be added to the system. There are comparable commercial benchtop scanners out there from a few different companies. The reason that we didn't use these are because of the higher cost and just the lower flexibility and transparency for the students. So we have this wiki site for the user community. So it is an open source design. And the wiki has a part list, board files, full sequences, and the MATLAB-based user interface code. And I think this is also linked in the open source imaging website that was talked about earlier. All right, so the motivation to develop these for educational use was to provide a hands-on teaching school of MRI principles, but also as a general tool for teaching basic engineering concepts like signal processing and data acquisition. The first application for these scanners, the reasons they were originally developed, was for an MIT undergraduate course that was introduced in either 2013 or 2014. And it was Intro to Electrical Engineering and Computer Science via Medical Technology. And so they were used in this class to teach basic concepts in data acquisition, computer control of experiments, signal processing, and Fourier analysis. And the pulse sequence and the data processing were all done in MATLAB. And we use the scanners to demonstrate concepts for induction decay, flip angle measurement, B0 shimming, gradient echo, spin echo, 1D projections, and 2D and 3D imaging. Since then, the scanners have been used in 5 other undergraduate and graduate courses at MIT, and we estimate that over 1,000 students have actually used the scanners over the last 10 years. So here are the major components of the scanner, and I'll talk about each of these in more detail later. But the first is the magnet, which is 0.18 Tesla. And we use the Medusa console, which was fabricated by Procyon Engineering. And then there's the gradient power amplifiers, and the gradient coils, and the RF subsystem, which includes the transmit receive coil and the TR switch and preamp board. And these components that I'm showing here are what were implemented in the original 20 scanners that were deployed at MIT. Since then, we have several new versions of various components in the scanner that we've developed here and other people have developed elsewhere as well. Graphic just shows the system assembly. So the main block there is the magnet. The gradient coils are planar gradient coils that are on PCBs that are stacked with these plastic spacers and fit into the bore. And then this that's showing now is the RF coil holder. Play one more time. There's the magnet, planar gradient coils, some spacers we use to position them correctly, and there's our coil and the coil holder, and that is the phantom that we use to do the imaging. So here's a picture of the complete system. So we used an enclosure that was constructed with out of a wooden box with brass foil for RF shielding. On the right, these are the gradient filters for the gradient lines coming into the box. On the shelf of the card is the Medusa console, and on the bottom is the gradient power amplifier box. And then on the right, you can see the inside of the box. So we have a little holder over here for the phantoms, the main magnet and the RF coil, and then inside the box we also have this little board that's mounted in there, which is the TR switch and the preamps. And on the outside, we also have the transmit RF amplifier. Okay, so B1 of the magnet, so this is the magnet design created by and built by the Chinese Academy of Sciences, and they built 20 of these that are at MIT now. And so, as Tom was saying earlier, these are more of a dipole design, a yoked dipole design as opposed to the Hallbox cylinder that he was talking about. But and these magnets as well, permanent magnets are used that are made of neodymium ion boron, and they're mounted to iron yoke pieces that contain and guide the flux lines. And the pole pieces that are on the other, so sorry, in this figure here, the red is the actual neodymium magnet, and the black part are pole pieces that help to shape the field and improve the homogeneity. So this magnet has a field of 0.18 Tesla with 50 ppm homogeneity and then 1 centimeter DSV. And it weighs 13 kilograms, And the gap between the pole pieces is 4 centimeters. That's the space we have to work with for the gradient coils and the RF coil and sample. This is the second version that we developed here at MGH, and it's the one that we're using, that we have here in the lab now, and we'll be showing in the demo today. And so it's the same basic design. We have a much bigger neodymium magnet though. So this one is, this one creates a 0.37 Tesla field as opposed to 0.18 Tesla. And we have about 40 ppm homogeneity in a 1 centimeter DSV. This weighs 24 kilograms. Do you want to take over now?
Sure.
Yeah.
I'll make a few remarks about the console. So the original console, as you can see here, had an RF waveform generator and independent boards for each gradient axis that then drove DACs on our gradient amplifier PCB, and then a control board. This Medusa console was controllable from MATLAB, which made it very convenient to generate user interfaces and to pipe the data back in for students to process it. You know, since introducing this setup, we've been moving forward using an open source console, the so-called Okra console, which Tom referred to in his talk. And here's a few references and links if you want to look at the details further. This supports up to about 50 megahertz operation with 2 transmit and 2 receive channels. And it's very much an ongoing process to collectively crowdsource pulse sequences and user interfaces for this red Pataya FPGA board. Here at MGH, we worked on a PulseSeq wrapper, which allows a version of this software called Marcos to be controlled from MATLAB via the PulseSeq interface. So then students can really easily generate pulse sequences using the PulseSeq format, and our wrapper will convert them to machine readable code for the red Pataya console. So this is also very much a work in progress and open for contributions from anyone. Moving on from our console to the gradient power amplifiers. This is a schematic of the first GPA board that we used. We tried to keep everything very low cost. So these are OPA 549 power op amps. They're about $20 each, 2 per channel. So that's the most expensive component. These are the 3 axes, X, Y, and Z. And then there are DAC boards here to generate the analog waveforms for each power stage. And then switching power supplies inside a box. So tried to really keep the cost down to $100 or $200 per channel, and still provide plenty of current for our imaging applications. And other open source GPA designs have flowed from this original concept, including GPA boards that have been used for B0 shimming applications as described here.
Right. The next major component to discuss is the actual gradient coils. So again, these were originally designed from collaborators at the University of Freiburg. They were actually the coil design was done there. The actual fabrication and implementation onto a printed circuit board was done here at MGH. And so these are shielded planar gradient coils for the X, Y, Z direction, and also there's a Z squared term as well for shimming. So the coils were designed based on a stream function method. You can see the reference here that used a similar method by the same group. The gradients were designed to be on a planar surface 1 centimeter from the isocenter, and then the shields were designed to be 2 centimeters from the isocenter. And the shields are right against the magnet poles, and so the reason that we're using a shielding layer for this is to prevent eddy currents in the pole pieces. The implementation of the current patterns was done on a printed circuit board, so it was actually done on 8-layer PCB boards with buried vias and 4-ounce copper traces. And the efficiency of the X, Y, and Z coils range from 10 to 14 millitesla per meter per ounce. So they're quite efficient. So next is the RF transmit and receive coil. So this is a very simple coil. It's just a small solenoid with a 12 centimeter diameter with 8 turns. tuned to the Larmor frequency, which in the V1 magnet case was 8.1 megahertz. The former for the RF coil is just 3D printed, and the whole thing is wrapped in copper foil for shielding, which helps improve the SNR quite a bit. And then inside, well, the coil is specifically designed to hold these 1 centimeter diameter tubes for the imaging phantoms. And so our sample tubes are then just these 1 centimeter NMR tubes that we fill with doped water. And then to create structure, we use these 3D printed phantom inserts to create different shapes. You can also see on the top there is a fixed mouse frame that we also did some imaging on. Okay, next is the RF subsystem outside of the coil. So we have this TR switch board. The TR switch is sort of the classic pin diode plus quarter wave design. In this case, we're using a lumped element quarter wave because the wavelength is very long for these frequencies. And so the pin diodes are biased during the transmit pulse with the TX gate from the Medusa console, and these 4 files are on the wiki. The transmit amplifier that we use is an off-the-shelf mini circuits amplifier that's low cost. I think it costs something like $100. I'm not sure. And then the preamps are these very small Galley 71 amplifiers that are also surface mount for mini circuits. They have 25 dB gain and a 2.7 dB noise figure each, and we use 2 stages of those in this for our preamp stage in this TR switch. Here's some example images. Just checking our time here. So here's some example images from the system. On the top, so first off, all the sequences that all these images were made using spin echo sequences. The top one is a 2D rare acquisition using 2D phantoms. The B and C are from 3D rare sequences. And so B is just a 3D printed phantom, and C is the actual mouse frame example that I was showing earlier. So here's another example from our paper. So A and B were acquired from a Bruker 4.7 animal scanner. C and D were acquired from our scanner, just to show comparable resolution that we're able to achieve here. So A and C are capillary tubes with a 1.8 millimeter OD and a 150 micrometer wall thickness. So we're able to resolve those here as well. And B and D are a nylon bolt with a thread spacing of 0.7 millimeters. Here's just some photos of the scanner in action. So here's Jason and I on the left delivering some of these scanners to MIT almost 10 years ago now. And on the right are the actual scanners in action, so being used in the lab by the students in 2014. So for the demo, I'll show you some of the GUIs we developed, so I'm not going to spend much time on them here. We made a GUI that demonstrated the free induction decay and shimming, and another one that showed spin echoes and 1D projections. I'll show you this lab in a minute also. And then we have also GUIs for doing 2D and 3D imaging. Okay, so I'm going to go actually now. Still with me. Go to MATLAB here, and I'm not sure if there's a way for us to see our camera, but here's our scanner here, and so here's the magnet and the RF coil.
Actually, Clarissa, could you maybe stop sharing your screen briefly so that we can see your camera window?
Okay, great.
That's better, thanks.
Okay, so yep. So here's our system. You can see the magnet and our RF coil, the TR switch here. We have the phantom holder, a few phantoms. Yep. Yeah, so I'm not 100% sure the best way to do this. I'll kind of just point it down here, and I'm going to share my screen again so you can see the MATLAB GUIs, I guess. Maybe you can point it down a little bit, Jason. No, this works. All right, so here is the FID GUI. So we have the center frequency
without repetitions.
So we have a frequency finder. We click here. We can run this, and it'll search for the center frequency. The field drifts with temperature, so every time we turn it on, the center frequency is a little bit off. So now it's found the center frequency. I can turn the repetitions, increase the number there, so you can see it kind of going. If you take the phantom out, you can kind of see it does in fact disappear. Oh, and also, so that we also have an auto shimming function here. I don't think it makes sense to run it now, but I can show you if we zero the shims. Our line width is broadened. If I move the shims again, we get the nice angle. And now we can, we also have the flip angle calibration that we can show.
Stop.
All right, so what this does is it just acquires the FID with increasing power levels. This has a fixed 160 microsecond hard pulse, and it's just increasing the relative amplitude of the transmit pulse. And so if we keep running this, we'll see it hit a 90 where we have the max amplitude, and then a 180 at the minimum, and then it'll keep going actually. So I'll just stop it once we kind of see a minimum here.
Okay.
All right, that looks good. So
switch to the 2-tube phantom.
All right, so so we have our looks like our best amplitude is about 0.15 here. Then now we'll move on to another GUI, which is the spin echo GUI. So this loads our center frequency for us. I'm going to input the RF amplitude that we just found was the best. And then I can run the scan.
Load the shim.
Yeah, and then we can load our shims, and it'll look a little bit nicer for us, hopefully.
The 2-tube phantom.
Okay, so this is a different phantom, so that's why the signal looks lower. So one thing we can do in this GUI is we can also, the students can change the echo time so they can see how the T2 decay changes. Do you want to actually put the other phantom just so we can see the signal a little bit better first? Okay, here's a nice signal. So then if we increase the echo time, we should see the echo amplitude here. We can they can start to get a better understanding of T2 decay. Okay, but we can go back. So we're going to put in another phantom in now that we do a lab in the class that's a mystery phantom, and so we cover it so they don't know what's in there, and then they can kind of use this GUI to try to guess what's in there without doing a full reconstruction. So I'm going to increase the repetitions here.
1D projection.
Oh yes, so we need to do a 1D projection along
X is good.
Long X.
You can reduce TE a little. 50. Stop and start. Oh, the readout is too long. It's 33 millisecond readout. Just make it like 3.
There we go. All right, so this phantom has 2 tubes of water in it. So Jason is now rotating the phantom, and you can see that some are a 90-degree rotation angle. It'll collapse into 1 peak instead of 2 peaks. And so in this way, the students can do sort of a projection reconstruction by hand to figure out what's in there. All right, so we're, I think, at our time now, but we can just quickly maybe do the 3D or the 2D imaging.
Yeah, let's try the 3D.
Okay, so let's just do the 3D imaging.
Space comes in.
You see the K-space data here. And all of these GUIs are also available on the wiki. So here's our 3D image of an MIT phantom. All right.
Okay.
All right, I think that's it for the demo. Just quickly go back and show a conclusion slide here. All right, so yeah, so we just demonstrated our tabletop scanners that are 0.18 to 0.37 Tesla. These were constructed with a budget of 10K each, and we have constructed probably about 25 of them total now, maybe more. And all of the information about these are available in the wiki and the paper I showed earlier. And yeah, they've been used by many students in different courses at MIT now. And there's also a lot of ongoing development from people at different institutes developing improvements for all the different components, including the console work that Jason spoke about, and also RF components and GPA designs, and I think also gradient and RF improvements are upcoming. Again, I just want to acknowledge all of the different institutions and people that helped with these scanners, and also thank you again for inviting us to give this talk and for everyone for listening. All right.
All right, that was awesome. Thank you so much. You're really making me wish that I was a student at MIT and take that course. So no questions yet, I don't think, but a quick question. I'm just wondering if you've had anyone reach out to you like for using this beyond educational purposes. Like showing that, what kind of made me think of that is when you showed the images that it's comparable to the Bruker system.
Yeah, I mean, I think the main purpose that we've seen is that it's been used to help develop these open source consoles. Actually, it's been sort of like a good test bed for those. I think that has been the main component that I think it's been useful for other sort of research prototyping so far. But you can imagine other projects that could come with this as well.
Yeah, and they're all open source designs, so you could actually build a commercial product largely based on a lot of these system components, and that would be fair game because it's all open source. But we haven't ourselves really pursued industrial uses of it.
All right, looks like we have a couple of questions. First, Lionel's asking about the magnet yokes. Do they improve the field a lot? Yes, do they improve the field a lot?
The yolks, yes, the yolks do improve the field. I mean, I think it'd be difficult to actually design this type of magnet without a yoke, but they do, like, the dimensions of the yoke and do factor into the magnet design and the homogeneity that can be achieved. The pole pieces also play a big role. So there's some iron pole pieces attached to the magnet faces, and those could also be optimized to shape the field and improve the homogeneity.
And the second question, what about designing bad quality components like gradients to show the student the effect of non-ideal systems?
Yeah, so we some of our magnets were not as well shimmed as others, so they did see some of those effects. We had some, there are 20 of these magnets, and some of them, there were a couple of them that I'm not sure why, but the shim was off a bit, and so yeah, they saw some of that, and sort of the limits of what you could do also with just B0 shimming to improve that. But yeah, no, I think that's a good idea, maybe for a more advanced topic for students.
Yeah, that would definitely be really interesting. Another question that I have, like, how difficult would it be to scale up this design to like a larger bore size? Or at that point, would you have to start thinking of different components altogether?
It's not. Everything just gets a lot bigger. I mean, I don't think there's any like significant changes in the design.
1 centimeter.
Yeah,
is what we're working with now. So for, it's about like a finger width or less. What we have now.
Yeah. So but really, like this, this design is sort of, it was meant to kind of include a conventional architecture, and it could be scaled up actually. And in fact, I think that the brain scanner that's being developed in Hong Kong, the portable brain scanner that's being developed at Hong Kong University, uses a somewhat similar geometry magnet. They use a yoke dipole magnet like this. It's just bigger, basically. I don't think that there's really anything else besides size and power.
The shielding gets a lot harder if you have a body sticking out of the magnet. We get away with this relatively simple shielding strategy because there's no sample extending far outside the magnet, the shielded box. The body has a way of piping noise into something like a head magnet. Also, the RF components, I think, would get a lot more expensive if you scale up, especially the RF transmit amplifier. We get away with this very inexpensive 1 watt amplifier, but once you go to even 10 or 50 watts, it's a big increment in price.
Okay, well, thank you again, Clarissa and Jason. Again, if you have more questions, feel free to keep putting them in the chat, and we can invite them back for discussion at the end of the next talk.
Thank you.
Thank you so much for the demonstration as well. That was very cool. All right, and our last speaker for this session is Philipp Amrein from University Medical Center in Freiburg, Germany, and he'll be talking about CoilGen, the open source MR coil layout generator.
So hello, can you hear me?
Yes, we can hear you.
Okay, and you also can see my presentation. Okay, welcome to my slides. I'll show you something about my work, which was developed.
We're still seeing the PowerPoint screen.
No, okay. Can you see the slides now?
Looks like still PowerPoint.
Okay, I hope it's I don't know why it does not work.
That's all right. We can make this work. As long as that's okay with you.
Yes. So it says to me I'm sharing my screen.
Yeah, you are sharing still the PowerPoint slides, but I think you can just get started with this. And that should be fine.
But you can see the slides, or do you? I don't. Where's the problem now? I don't understand. So you can see the different slides, right?
Yes.
Okay. So I just go with it. I'll show you my my work about open source project, which is intended to facilitate the design of grading coils, and it has a focus on post-processing. And by far, it's not the only tool that is out there, but yeah, we try to make it open source available and simplify the design process. So as you already know, the MR scanners can be thought of as an onion of coils, and the different parts has already been explained. And the gradient coils are located between the main magnet and the
Philipp, sorry, we are still seeing your PowerPoint window. Oh, now it changed. Sorry. Okay, go on.
Okay. I'm sorry for the problem here. Okay, can you see the slides?
It's still only the PowerPoint window.
Okay, I try to share then this thing. So is it now working?
Yes.
Okay.
Perfect. Thank you.
Okay, great. Sorry for the interruption. Yeah, so it's about gradient coils, and they are located between the main magnet and the RF coils. And as a note on theory, why you need gradient coils, in MR we acquire the magnetic precession via the Lama frequency, and it in itself it has no spatial information. We have to encode it via additional fields, and we call them the gradient fields, and they are linear fields in the different coordinate MR coordinate directions, so it's X, Y, and Z. And with this spatial encoding, we can move through K-space and sample our data. And such a linear field is typically specified within a certain diameter, which is the region of interest. And for example, a whole body scanner has a region of interest of like 20 or 30 centimeter DSV. And why should we still work on gradient coils? I thought about it, and I think everyone who has some experience with scanners knows that if you enter a room, there's a lot of RF receive coils for tailored to specific body parts, but you will not find any or probably not find any specific grading coils, local grading coils, and that's actually a shame because they would have been the sensitivity which gain you get by bringing your grading coil closer to your target region is more than there can be orders of magnitude. So one big potential of gradient research would be local gradient coils, because you really can do something which is not possible with the whole body gradient system. And if you want to design a gradient coil, you can you have to do some pre-considerations. So first, of what kind of what do you want as a application? Is it you are interested in resolution or specific contrast? And this all defines the target field which you want to have. And in the target field goes the linearity and also the efficiency of the coil is there, can be specified, and it will determine what of encoding capability you will have. And then you should think about on what kind of geometry you optimize your coil. So for a standard gradient system, it's the cylinder, but not necessarily. There are already commercial systems which are based on biplanar or open configurations, or even there's also monoplanar gradient coils. They all have benefits and drawbacks. And finally, you should think about what are your limitations. So there are always hardware limitations, which are determined by the amplifier you have, but there are also biological limitations. So by switching the gradient coil, you will induce electric fields, and then this might give rise to PNS stimulation, nerve stimulation. So it's these are the limitations. So this all goes into your design process. And in my work and the code repository, we are using the stream function method. It's not a new invention. It has been already published in the early 2000s. I won't go into detail here, but it allows to find a flexible current density distribution on a meshed surface, and it works with little basis function, which are like you can think about microscopic currents about your mesh nodes, and the optimization process is then solving the equations and getting a stream function, and this stream function is not directly the coil you get, but it's an indirect quantity. You then have to discretize it, this stream function, and to build your turns and the wire trace from that. So, so the optimization part in the stream function approach would be to solve the equations, get your stream function, and then there are post-processing steps which gives you the final layout. And in the code repository, it goes like this, that you define all your geometry parts, your target fields, and you solve the optimization problem. That gives you a stream function, and this stream function itself is not the coil. So you I add one new step. It's to convert your 3D surface into a 2D domain by means of parameterization. And in this domain, we can calculate the isocontour lines, and when they are on this flat domain, it's easy to find a spatial relation between the lines. So we can group them and then do the interconnection part. So the stream function has to be discretized, which means to find the windings that match the stream function. And these windings are loops, non-interconnected loops, and there has to be some interconnection routine to obtain a intersectionable wire trace. So this is all done in the code. So the idea is really here to only specify your target field, geometry, and then do the code, do all the rest, and then also plot the result in terms of what is the gradient strength you obtain and so on. And here's some example on a transverse gradient. Looks a little bit complicated, but so it's now again in this 2D parameterized domain, and we see the stream function. It will be interconnected. First, there will be some grouping done, so you see the 4 quadrants, but it can be actually any topology. It will find the relation of these groups, and then these windings, these isocontour paths are groups are interconnected and then warped back into the 3D domain. And also one aspect which helps us a lot is that we can not only solve this problem for one set of input parameters, but we can make a loop over it and so find our the best set of parameters which match our specifications. For example, sometimes you might ask, okay, what is the number of turns I need to obtain a certain field fidelity? And we can simply iterate over the number of turns and see that, okay, we need like 20 or 30 turns, and our error is then dropping below 1%. However, everything comes with a cost. So with the number of turns, we also get the rise of coil length and inductance. So yeah, that would be one application of this code, that you can sample over your inputs and just not only calculate one coil layout, but many, and then choose the best which matches your needs. Okay, there's another more complicated application of a plane-specific stimming coil, and here you really can see that sometimes the layouts and the topology gets really complicated, and that's also one reason to do the automation. It's yeah, a lot of work to interconnect these, and to see that with this means of the topology grouping, we can find a reasonable way to connect these loops without adding too much return paths and so on. Okay, how to use it? You can go to it's all open source. Go to the GitHub homepage, and unfortunately it still runs on MATLAB, but internally we are thinking about converting to Python, and there's also some work being done to get it to Python, so that you don't need the proprietary MATLAB software. And you then, but now it's still on MATLAB. You download the repository. You can open. So yeah, you go to GitHub, download the repository, and then you can open the example folder, and there you see some different applications, and you open it and run it on MATLAB, and it should work and give you some layout. And you also see on here that you have a lot of freedom in adjusting your inputs. So there's a lot of input parameters, and if you really want to understand them. So I would advise you to go to the sub-functions and check the past inputs, because there it's a little bit better explained what they are doing and what does it mean to change them and so on. And one nice also, I think, good feature is that you can not only change your target fields, you can also work on your current plane surface. But I also mentioned you have to find the geometry, and for these three examples, for the monoplanar surface, the biplanar surface, and the cylinder, there are internally functions which are fully parameterized. So, for example, there's a function, it's called create mesh, cylinder mesh, and there you only need to specify the height of your cylinder, the radius, the number of nodes, so which gives you, with the number of nodes, you can play with the resolution or the fidelity of your grading coil, but it also decreases the computational effort. And furthermore, you can specify the orientation of the cylinder. So here you see in the last 4 inputs, there's these vector entries. So it's you can rotate your cylinder in any direction you want, and just with that rotation, you can go from a normal gradient to a Halbach gradient by rotating the cylinder for p-half. So it's just one change of the input, and you get the Halbach configuration. And we also thought about what can we add to the project to simplify the manufacturing. And by rapid prototyping, there's some manufacturing methods which you could use, and you need the right file formats to apply these methods. For example, for 3D printing, you would need an STL file, or laser cutting, you would need some vector graphic and so on. So we add also some capability for that. For example, we add a sweeping capability, where you would get from the wire trace a 3D volumetric conductor. So you can specify a cross section, and you get an STL file. And this STL file you can not only use for the manufacturing by subtracting it from your support geometry and then print it. You can also use it for modeling, final element analysis, like heat analysis and so on. So it gives you the 3D model. And also, if you specify it, you can also get some kind of a PCB layout. So we use that for one project where you, for example, this transverse gradient, you can optimize the gradient and then use the outputted 3D vector graphic. And here's a little, in this approach, the interconnection is a little bit different. It has like 2 layers. So it's this spiral in, spiral out approach. So it helps you to reduce the number of feeding wire paths. And so you get, for each contour, you get, for each group, you get a spiral in group, spiral out group. And these are then, you get 2 layers which you need to print via PCB. And so the projects which was for which this code was developed is the initial one was the press coil diffusion coil. Here the code was more used for the post processing, and the together with my colleagues, and for the optimization, it was not used in this case, but we use it for the post processing to get a support body files and printed them, and then you see on the image on the photograph that the body is printed and the wires then pressed into this printed body. And also, which another project was So these are all work from my colleagues, Sebastian Litin and Tom Gier. And another cooperation project was an updated version on this tabletop gradient system. Clarissa already mentioned it, that there was a collaboration with Freiburg, and we now have a new version. And it was from the University of Magdeburg. Markus Prier also built a tabletop scanner with that layout. And you can see it's realized via this PCB approach with the two-layer. And if you each channel has actually, it's a little bit complicated. It has it's biplanar gradient system, so it has each channel has an active two planes and also an active shielding layer. So yeah, it's a lot of traces. And another collaboration now, which is also built, is for which we use the coil code. It's the open source scanner with the PTB in Berlin and with Lukas Winter. And here we designed a gradient Halbach configuration for a gradient system for the Halbach configuration. And it's now being built at the moment. So yeah, that's it. If you have any question, I'm happy to help you. And if you want to try out the coil code, just download it. And if something's not working or you need any help, feel free to contact me. And I'm really eager that it's being used and it continues getting developed and new ideas and so on. And thank you.
Great, thank you so much for your talk. It's really cool to see how this can be used in different applications. I guess besides some of the applications you've had in your talk, are there any other ones in the works, like any other like specific anatomies that CoilGen has been used for?
Yes, we are now working on a dedicated dental grading system, and it has some trying out some ideas about also nonlinear encoding with curve slices for dental MRI. Furthermore, we are working on a knee grading coil dedicated on a human knee, and these are two projects that are now being done.
Do you have to take into consideration like the other coils that would be in the system, like the transmit, receive, etc.?
Yeah, good question. Yeah, they might, depending, for example, local grading coils might shield your body RF coil. So they should come together with also dedicated RF system. So it probably would not work just to add a local grading coil, because it's interfere with your body RF coil. So it has to be designed, and the concept has to be made together.
I also wanted to mention just how cool it's been to see how all of the different speakers have different aspects of their projects have come from each other and the collaborations between the groups. That's really cool to see.
Yes, it's a mutual benefit. So also sharing your work is really it comes back to you in a positive way. So also that's why also I would like people to use it, or if they find some error or some other idea, it's meant to be a community project.
We have a question in the Q&A. I'll put this on the screen. Just out of curiosity, do you think this software could also be used to simulate RF coils in the low frequency regime?
That's a very good question. I was thinking about it. To use it actually in the first approximation, I would think so, because when the wavelength is long, you can go to the stationary regime. There might be some internal, you would, I mean, now I calculate the sensitivity matrix and the stream function negative entity in the stream function approach with the Biot-Savart law. There is, you could think about going to the retarded Biot-Savart law for the frequency RF domain. Maybe I would think so. But it might be interesting to work on that. I also would be happy if someone would adjust the code to work on RF coils. That would be really cool. I think from I mean, this project is mainly about the post-processing, and there you can also benefit for the RF coils. But it does not model lumped elements. You cannot, for example, a birdcage has the capacitors, and there's no in such an approach, no way to take them into account. But for low frequency.
Well, it's very cool to think about the different ways that code could be used. So again, if there's any more questions for any of the speakers, they are all still here. But otherwise, we're just about out of time. So I want to remind everyone that there are some more talks later today to check the schedule. I think that's everything. Thank you again, all of you, for your time and your excellent talks.